Imagine finding a fish sealed beneath desert-hard mud. No pond, no food, no visible movement. Then rain touches the ground, and the creature wakes. This is not a movie monster. It is an African lungfish. In exceptional conditions, this fish can remain dormant for years. Reports commonly cite 3 to 5, without open water or a meal. 4 years sounds impossible, because for almost every fish on Earth, it is. African lungfish live in freshwater swamps, rivers, and floodplains across sub-Saharan Africa. During the wet season, they swim, hunt snails and insects, and rise to the surface to gulp air like no ordinary fish. Look closely and it seems almost prehistoric. A long, muscular body, thread-like fins, and a wide mouth. But its strangest equipment is hidden inside. True lungs that let it breathe oxygen directly from the air. When the rains stop, shallow pools shrink under brutal heat. Other fish must escape or die. The lungfish reads the warning signs and begins a survival sequence refined across hundreds of millions of years. It pushes headfirst into soft mud, twisting and forcing a narrow chamber around its body. Before the ground becomes solid, it leaves a tiny passage connecting its mouth to the air above. Next comes the cocoon. The fish releases layer after layer of mucus. As the mud dries, that mucus hardens into a thin protective envelope with one small breathing opening near the mouth. Inside, the lungfish curls tightly and switches into estivation, summer dormancy. This is not normal sleep. Movement nearly stops, breathing slows, and the body begins an extreme program of energy conservation. The pool may disappear completely. Above ground, the surface fractures into plates. Yet below it, the fish remains alive inside a humid pocket, isolated from the world, except for its narrow airway. Most fish pull oxygen from water using gills. African lungfish can rely heavily on paired lungs instead. Air travels through the passage, enters the mouth, and reaches those lungs, even after the surrounding mud turns hard. Their gills still work in water, but air breathing is essential. In fact, an African lungfish can drown if denied access to the surface. It is a fish whose survival depends on taking a breath. That solves oxygen, but not hunger. With no meal coming, the fish lowers its metabolic demand and lives on stored energy. Every unnecessary process is reduced, while vital organs keep operating at a minimum. Think of metabolism as a biological power bill. During estivation, the lungfish shuts off the lights, lowers the thermostat, and runs only the systems required to stay alive until the drought breaks. Over a long dormancy, it loses body mass and uses its own reserves. The goal is not comfort or growth. It is to spend energy so slowly that months, and in extreme cases, years can pass. Waste creates another deadly problem. Aquatic fish usually release toxic ammonia into surrounding water. With no water to carry it away, the lungfish changes its chemistry, producing less toxic urea that can accumulate more safely. The cocoon is more than dried slime. Research has found immune cells within it that help trap bacteria. The lungfish appears to build not just a sleeping bag, but an external layer of biological defense. Microscopic immune cells migrate toward the skin and into the cocoon. There, they form web-like traps around microbes, helping guard a motionless animal that cannot escape infection or repair damage in the usual way. Days become months. Seasons may turn. The creature does not drink, hunt, or make a dramatic move. Its greatest survival skill is patience, remaining sealed in darkness while the landscape above stays hostile. The famous 4-year claim describes an extraordinary upper-end survival ability, not every dry season. Natural dormancy is often much shorter. Still, even surviving many months in hardened mud is astonishing for a vertebrate fish. Then the sky changes. Heavy clouds gather over the floodplain. The first drops vanish into dust, but soon rain fills cracks, softens the soil, and begins to dismantle the lungfish's underground prison. Moisture reaches the cocoon. The fish rehydrates, its breathing increases, and dormant systems restart. The envelope softens as the chamber fills. A body that seemed lifeless begins to bend and push. Finally, the lungfish breaks free. It wriggles through wet mud into new water, gulps air, and resumes swimming. After an immense pause, its biological clock is running at ordinary speed again. Recovery is not magic, and the fish may be lean, but it can feed and rebuild. The same animal that waded beneath a dead lake is once again an active predator in a living wetland. Lungfish belong to an ancient branch of vertebrates. Fossils show their relatives existed hundreds of millions of years ago, long before dinosaurs, when animals with limb-like fins and air-breathing abilities were reshaping life's possibilities.
Modern lungfish are not our direct ancestors, yet they offer clues about the transition from water toward land. Their anatomy carries an evolutionary echo: gills, lungs, fins, and a body built for unstable habitats. Scientists study estivation to understand how organs survive inactivity, dehydration stress, waste buildup, and reawakening. Those questions could matter for intensive care, tissue preservation, muscle loss, and other medical challenges. And then there is Mars. NASA has funded early-stage studies of animal torpor and spacecraft concepts for human stasis. Lower metabolism could, in theory, reduce food, space, and psychological strain during a long voyage. But here is the fact check. NASA has not announced a program to copy lungfish biology into astronauts. Human hibernation remains experimental, and putting healthy people into months of safe torpor is far beyond current medicine.
The risks are enormous. Muscle and bone loss, blood clots, infection, radiation, brain effects, and the challenge of waking reliably. A spacecraft would need automated life support able to handle emergencies while its crew could not respond. Still, nature proves that radical metabolic slowdown is possible in a vertebrate. The lungfish does not give engineers a ready-made blueprint, but it gives science a living question. How does a body pause without falling apart? From a cracked African floodplain to a future spacecraft, the connection is not science fiction. It is scientific inspiration. One animal survives by carrying water, air, energy, and immune protection in precisely balanced systems. So could humans someday sleep their way to Mars? We do not know. But beneath the mud, the African lungfish has already mastered its own form of time travel. Shut down, hold on, and wake when the world returns.